we are finally at a point we get to one of the most important theorems in calculus, hence why it's called the fundamental theorem of calculus. And this is where we take the concept of an antiderivative and relate it to the definite integral and the area under a curve. So far we've learned the area under a function f from a to b is given by that definite integral where you go from a to b of your function on the inside. So in this section, we're going to relate the antiderivative to the integral. So we're going to start by really looking through an example. I'm going to evaluate an integral from 0 to x of the function t dt, where x is any real number as long as it's non-negative. And so this is something we can really do geometrically because the function on the inside is quite nice. So if we interpret this in terms of area, the integral is the area under the function y equals t from 0 to some arbitrary x value. So if we go ahead and graph that, we've got y equals t. It is just a nice function. I'm going to go from 0 to some x value. And so the area, or this integral, is really just a triangle. And so the width of this triangle is going to be x. And the height, if you plug in x to this function, the y value is also x. So its height is x as well. So since this area is just a triangle with base x and height x, the integral from 0 to x of the function t is going to be 1/2 the base times the height, which is 1/2 x squared. So I'm going to call this g of x because it really depends on the x you want. So basically this just gave me kind of a function. If I wanted the area under the curve from 0 to 3, I could plug 3 in here. If I wanted the area under this function from 0 to 7, I would plug 7 into here, and that would tell me the area under this curve. The thing we can notice though, the function on the inside is t. If I think about the antiderivative of t, it's 1/2 t squared, which is exactly what this area ended up dealing with. So the thing you want to notice is if this is our function g of x, 1/2 x squared, then its derivative is exactly x. So g is an antiderivative of the function y equals x, which is exactly the function that's inside our integral, or our integrand. So really, there is a really nice connection relating this integral to the antiderivative. And that's what this fundamental theorem of calculus goes through. There's ultimately 2 parts to it. The first one is exactly this. It tells us that this integral is an antiderivative of the function. The second is going to be a way to evaluate a definite integral using the antiderivative. So you're going to see this abbreviated pretty frequently as just FTC, just like mean value theorem is MVT. So if you see that, don't be concerned what it means. Okay. So what the fundamental theorem of calculus part 1 states is if you have a function as continuous on the interval from a to b, the function g defined by g of x equaling the integral from a to x of f of t dt, where x is some number between a and b. This is continuous on the interval ab. It's also differentiable, and its derivative is given by g prime of x equaling f of x. So basically, the reason we change this variable in here is purely so you don't have x's inside the integral and on the outside. What this means is that I can find a function that gives me the area under this curve from a to any point I want. So I'm able to get a function that will give me the area in return. So it's kind of like relating that indefinite integral to the antiderivative. It's just giving you a starting point of a. So let's try an example. We're going to find the derivative of this function. if you notice, the function we're differentiating is h of x. The variable is inside our bounds, okay? It has nothing to do with this expression here. Ultimately, the derivative will, but this has nothing to do with the variable x. This expression is an antiderivative of f of t. So if I differentiate the antiderivative, it's going to land me back to the function I started with. So ultimately, if I differentiate this expression, I'm just going to replace the t on the inside, which is my dummy variable, by x. So thinking of this example, because the function on the inside is continuous, by the fundamental theorem of calculus part 1, if I want to find h prime of x, all I'm going to do is evaluate this function at x, okay? Because I'd find the antiderivative and then I'd differentiate it again, and I would land right back to the function on the inside. Realistically, I know this can be hard to see, so the second part probably going to be a little bit better for finding derivatives like this. So we're going to come back to this example really soon. The second part of the fundamental theorem of calculus tells you how to find a definite integral. So as long as your function is continuous on the interval from a to b, then if you want the area under the curve from a to b, what you're going to do is find an antiderivative of the inside function, and you're going to evaluate it from a to b. And what this bar means is I'm going to plug in the upper bound, so I'm going to evaluate the antiderivative at b, and I'm going to subtract evaluating the antiderivative at the lower bound a. And again, you can pick any antiderivative you want. It does not make a difference. Okay? So to relate it to the very first thing we did, if we want to go through and find the antiderivative of this and use the fundamental theorem of calculus, antiderivative of t is 1/2 t squared. And I'm going to evaluate it from 0 to x. So what we do is we plug in x to give us 1/2 x squared and subtract plugging in 0 into this expression. And then 1/2 0 squared is just 0. So you get exactly what we did before, just using the area definition instead in those geometric formulas. Okay. As another short example, if I want to find the integral from 0 to pi of sine of x dx, that's finding the area under sine of x over 0 to pi. One antiderivative of sine of x is negative cosine. So the derivative of negative cosine is positive sine. And we're going to evaluate this from 0 to pi. So I first plug in pi, and I subtract plugging in 0. So cosine of pi is -1, but the minus out front makes it positive. So we get +1. Cosine of 0 is 1. So minus -1 gives you +1. The area under the sine function from 0 to pi is 2. Okay. The other thing you can notice is that, remember when we took the integral, we always tacked on that plus c. We don't need to worry about that when we're dealing with definite integrals. And I'll show you why, just utilizing this example here. So the most general antiderivative of sine of x is negative cosine of x plus c. So if I go through and use that fundamental theorem to evaluate this definite integral from 0 to pi, I could put the most general antiderivative and evaluate it from 0 to pi. But if you plug in pi, you're going to get negative cosine of pi plus c. And then when you plug in 0, same thing, negative cosine of 0 plus c. And then if you simplify this, negative cosine of pi is +1 plus c. And then you get negative cosine of 0, which is -1 plus c. If you distribute that minus sign, it ends up with plus 1 minus c. And then ultimately, these values of c just cancel out, and you still get 2. So really, it makes no difference what you pick to be c. It cancels out because when you evaluate it at the upper bound, you get the positive version. When you subtract the lower bound, you get the negative version, and it cancels. Okay? So when you have limits of integration or bounds to represent that area, you don't need to worry about it. But if there were no limits, remember that's asking you to find the antiderivative, so you would still need the plus c. Ultimately, a definite integral is representing the area under the curve, so this definite integral should lead to a constant, while an indefinite integral will result in a function, or the antiderivative. Okay? So this method, way easier than trying to go through that limit definition of the sum of those approximating rectangles. But you can't go through this method until you've seen where this comes from. So all of these theorems stemmed from that formal definition. But let's get some more practice, because this is definitely way easier to go about finding that area under the curve. Let's evaluate the integral from 1 to 2 of 4 plus u over u cubed du. So again, what I want to do is I want to find an antiderivative, evaluate it from 1 to 2. But in this current form, I can't find it, so let's go ahead and split it. We got 4 over u cubed plus u over u cubed, and we're going to integrate with respect to u. Thinking of how this simplifies, this would just be 1 over u squared. So if I have 1 over u squared, you can rewrite that as u to the negative 2. 4 over u cubed is 4u to the negative 3. Now, each of these I'm able to use power rule for, or reversing power rule. So the antiderivative would be you bump up the power to be negative 2, divide by the new power. If I'm finding the antiderivative of u to the negative 2, I bump up the power by 1, divide by the new power. And then the fundamental theorem of calculus tells me I'm going to evaluate this from 1 to 2. Before I try to plug in numbers, let's go ahead and clean these expressions up a bit. So if I do 4 divided by negative 2, it's going to be negative 2. U to the negative 2 can be brought down. Likewise, I've got negative 1 in the bottom, just bringing it to negative 1 out front. U to the negative 1 is 1 over u. And then we want to evaluate this from 1 to 2. So I start by plugging in 2, which will give us negative 2 over 2 squared minus 1 over 2. And I want to subtract plugging in 1, which will be negative 2 over 1 squared minus 1 over 1. So if we go through that, 2 over 2 squared is 2 over 4. So that simplifies to negative 1/2 minus 1/2. And then negative 2 over 1 squared is negative 2 minus 1. So cleaning all this up, the first piece, negative 1/2 minus 1/2 is negative 1. And then negative 2 minus 1 is negative 3. But that extra minus out front gives you a positive 3. So ultimately, we end up with 2. So the area under this function over the interval from 1 to 2 is 2. Now let's go back to finding those derivatives, and I think this will help make a little more sense. And we're going to even beef it up a step. Instead of just putting an x up here, we're going to do x to the 4th. Okay? So we need to really use chain rule in combination with that fundamental theorem of calculus, because I don't have just x up here. What I'm going to do is go through the process to show you what this looks like, and kind of then tell you in general what the derivatives of these things are. Because the variable is x, and that x is in the limits of integration. Again, this dummy variable on the inside is just telling you I'm going to take the antiderivative of secant of t with respect to t. So when you move on to multivariable functions, you'll know which variable you're integrating with respect to. So what I'm going to start with is this is little h of x. I'm going to let h of t be the antiderivative of the thing on the inside. I have no idea what function has derivative secant of t. All I know is h of t will be the antiderivative, so when I differentiate it, I land back at secant of t. So applying this fundamental theorem of calculus, the function I'm given is this integral from 1 to x to the 4th of secant of t. Utilizing that idea, it's going to be the antiderivative of secant, which I'm calling capital H, evaluated from 1 to 4. So ultimately, I'm going to evaluate my antiderivative at x to the 4th and subtract evaluating the antiderivative at 1. So if I want to differentiate h of x, it will be exactly the same as differentiating this piece. So this tells us h prime, which is what we're searching for, is the derivative of this piece using that fundamental theorem of calculus. Now for our derivatives, I can go ahead and take the derivative of each of these individually. And applying my chain rule in a general sense, I differentiate the outside, keep the inside, chain rule, differentiate the inside. When it comes to h of 1, that's just a number. So its derivative is 0. So ultimately, the thing I'm searching for is going to be the antiderivative's derivative evaluated at x to the 4th, and then multiplied by the derivative of x to the 4th, which is 4x cubed. But going back, h prime of t is secant of t. So really, I'm going to take the secant function and evaluate it at x to the 4th. So that piece just gives me secant of x to the 4th times 4x cubed. So ultimately, the derivative with respect to x of this integral cancels the integral out, and I'm just getting that secant, but it's evaluated at this function up here. So it's secant of x to the 4th. And then chain rule, I pop the derivative of the x to the 4th out. So I get 4x cubed. We're going to look at another one before I go ahead and try to do the most general form for it. Now instead, I'm going to reverse these roles, and I'm going to have x to the 4th in the bottom. Same idea is going to apply. If I want to find the derivative, I go ahead and differentiate the antiderivative. The only difference is these bounds have switched, so these switch. So this function would end up equaling h of 1 minus h of x to the 4th, because that's the lower bound, okay, where h is that antiderivative. So I can go ahead and differentiate each of these separately. Again, derivative of a constant is 0. For the second piece, I work from the outside in. So I differentiate the outside, stays evaluated at x to the 4th. Chain rule, have to times by the derivative of x to the 4th. And then ultimately, h prime is secant. It's just going to be evaluated at x to the 4th. So if you notice, you really get the same thing. It's just negated, and that's because it was on the bottom. And with that fundamental theorem of calculus, you subtract plugging in the bottom. Okay? So in general, if I want to take the derivative of a function where my variable is in those limits of integration, okay? And I could have a variable in the top and a variable in the bottom. Thinking of this fundamental theorem, you'd find the antiderivative of f. Then you're going to evaluate it h of x and g of x. But you will differentiate it. So ultimately, I'm going to take the inside function and evaluate it at h of x. but chain rule is going to have me take the derivative of h. Then we subtract the function on the inside evaluated at g of x, and chain rule, I get the derivative of g of x. So let's try an example. Let's go ahead and find the derivative of this function where I've got the variable in the top and the bottom. So applying this same process, f prime, is I take this inside function, evaluate it at sine of x. So that gives me the square root of 1 minus sine of x. Chain rule, multiply by the derivative of sine of x. Then I take the square root of 1 minus t, evaluate it at x squared, and we're going to subtract that. So I get the square root of 1 minus x squared. And then chain rule, I take the derivative of x squared. So going ahead and taking those derivatives, I get the square root of 1 minus sine of x times cosine of x minus the square root of 1 minus x squared times 2x. All right, let's try another example. What is wrong with this equation? So if I want to find the area under the curve x to the negative 4 from negative 2 to 1, I go ahead, bump that power up by 1, divide by the new power. Fundamental theorem of calculus tells me I evaluate it from 1 to negative 2. And so if you want some more steps in here, that would be you plug in 1, so 1 to the negative 3 over negative 3, minus plugging in negative 2. And if you simplify that, you can trust me, it does end up equaling 3 over 8. Okay. But the problem with this, if you think of this function, that is 1 over x to the 4th. And so ultimately, there are two things that are wrong with this. If you think of the graph of 1 over x to the 4th, it's always positive. And somehow that's telling me the area under this curve is negative, but it's a positive function. The main issue is with this denominator. So x to the 4th has a problem at 0, because if I try to plug in x equals 0, I will divide by 0. So really the main issue is the fundamental theorem of calculus applies to functions that are continuous on an interval. But this function has a discontinuity, has a vertical asymptote at x equals 0. So really I cannot apply FTC. Other thing is 1 over x to the 4th is always positive. The area under this curve should be positive. But by going through this, you get negative 3 over 8. It is impossible for a positive function to have negative area. Okay? So this only works when the function is continuous and nice. That is when you can find the area underneath it. So we've got two more applications of these integrals here that come as a result of the fundamental theorem. The first one we're going to talk about is an average value. So if a function is integrable on the closed interval from a to b, then the average value of a function on this interval is going to be the area. So you're going to integrate from a to b. And think of your average value. It's typically like you're summing up a bunch of things, dividing by the number of things you sum by. We're going to find the area, and then we're going to divide by the length of the interval that we found the area under. So if you think about just an example for this function, you've got these y values that go up, they come down, and then they go back up. Basically, there's some number in there that's the average of every single one of these y values. And the problem is there is a lot of y values inside the interval from a to b. Your normal average, you sum them all up, divide by the number. So here, if I'm summing up all of these y values, it's actually finding the area under this curve. And so what we can do to actually figure out why this is the case is if we think of the average of ny values, we'll call it an. It is the sum of every single y value possible divided by the number of y values you took. And so that's really just a summation from 1 to n of your function evaluated all these x values. So this is all the different y values you have times 1 over n. And if I manipulate this a little bit and multiply by b minus a over b minus a and pull the denominator 1 out, that would leave me with the sum of my function evaluated xi times b minus a over n. And that's exactly delta x. So basically, if I take a selection of x values, add up those corresponding y values, and divide by the number of values, that gives me an approximation. But I need to take all of these, so I need to let n approach infinity for this. And when n approaches infinity, that turns into the integral. So basically, there is a number here somewhere that is the average value that your y takes. And so it would represent the area under this curve. Still end up being the same thing. So ultimately, this really is a formula we plug and chug in. Let's find the average value of this function over the interval from -2 to 2. So what we do is we want to find the total area of this function from -2 to 2. And I want to divide by the length of the interval. So the length of the interval is 4. And then we're going to find the integral from -2 to 2 of 4 minus x squared dx. So that's really just 1/4. If I go ahead and find the antiderivative of 4, it's 4x. Antiderivative of x squared is 1/3 x cubed. And then we're going to plug in from -2 to 2. So if I plug in +2, it'll give me 4 times 2 minus 1/3 times 2 cubed, which is 8. If we plug in -2, it's 4 times -2. And then -2 cubed would be -8. So it cancels and gives you +8 at the end here. And then it's just a matter of simplifying. So that's 1/4. 4 times 2 is 8. 8 times the third is 8/3. Then if you distribute this minus sign as well, this first one will be positive. This second one will be negative. And then ultimately, that's 1/4. You'll have 8 plus 8, which is 16. Minus 8/3 times minus 8/3 is -16/3. You can make this have the same denominator by multiplying by 3 over 3. So that would give you 48 over 3. And then you can subtract the 2. And this simplifies really nicely to 8 over 3. So the average value of this parabola over the interval from -2 to 2 would be 8 over 3. The last thing we're going through is the mean value theorem for integrals. And what this states is if you have a continuous function on a closed interval from a to b, then there exists a number c inside that interval such that, if you think back to our mean value theorem, it was the difference in our x values was equal to that derivative. So it's kind of like now, if I'm instead looking at the difference in my function, it's equal to its derivative, so that would cancel out the integral. So this tells me if I find the total area of my function from a to b, it's going to equal my function evaluated at some value c times b minus a. So really, what does that mean? It kind of looks similar to the mean value theorem that we're used to, but not 100%. So let's kind of think of it in terms of an actual function. Basically, what this is telling me, remember this left-hand side is exactly defining the area under this function from a to b. So ultimately, the left-hand side of this result from the mean value theorem tells me the area under my function is equal to something else. B minus a is exactly the length of this interval. And then I've got some value f of c. So basically there exists a c somewhere in here, so that if I go ahead and evaluate my function at that point, and I draw a nice straight line through it, this would give me f of c as this height. So it's telling me there is a point somewhere inside A to B that if I find the area of this rectangle, which will be f of c times b minus a, it's exactly my total area. So we call this the area of the mean value rectangle. Basically, the area you have can be compressed into a nice rectangle, and the height is an actual output of your function somewhere in between a and b. Okay? But again, this only works if your function is continuous on that closed interval. So let's go through an example. Let's find the values of c guaranteed by mean value theorem for integrals over this given interval. And the function we're dealing with is the square root of x over the interval from 4 to 9. So before I can jump into this conclusion that I'm guaranteed, I need to make sure that my function is continuous on this closed interval. And for us, we have a square root function. It has no issues whatsoever on the interval from 4 to 9, so we absolutely can apply this mean value theorem for integrals. So what this tells us is there is a number in between 4 and 9, so that if I find my total area, it's equal to my function evaluated at c times the length of the interval. Okay? And so what I want to do is find this value of c that makes this statement true. To do that, I've got to figure out what this integral even is. So I want to find the area from 4 to 9 of the square root of x dx. So that's just a matter of reversing our power rule and going ahead and applying the fundamental theorem of calculus. Square root of x is x to the 1/2. So to find the antiderivative, I add 1, divide by the new power, and then I'm going to evaluate from 4 to 9. Dividing by 3/2 is the same thing as multiplying by 2/3. So we plug in 9, subtract plugging in 4. And so that's 2/3. If you go ahead and deal with this 2 in the denominator, that's saying take the square root of each. So this would be 3 to the 3rd minus 2 to the 3rd, which is 2/3 times 27 minus 8. So that becomes 2/3 times 19. So in total, this is 38 over 3. So ultimately, this left-hand side, the total area is 38 over 3. I want to find the value of c that I plug into the function so that I can get 38 over 3 as an output after I multiply by 5. So kind of putting the pieces into this equation, 38 over 3 is going to be my function evaluated at c times the length of the interval. So 38 over 3, my function is the square root, so that's square root of c times 5. If we divide by 5, that's 38 over 15 is root c. So ultimately, the c I'm guaranteed is 38 over 15 squared, which roughly is around 6.42.